All right, let's talk about something really important. It's the one thing that separates a system that just succeeds from one that actually survives its own success. We are diving deep into designing a rate limiter. And look, this isn't just some boring traffic management thing. No, this is about architecting a system that doesn't completely fall apart the second you get that big win.
So I really want you to think about this question for a second. Is your system built to handle success or just to get there in the first place? Because let's be real, building a system to succeed, that's the bare minimum. The real challenge, the architect's challenge, is building it to handle that success. What happens when your app goes viral? A million users just show up overnight. Is that a party? Or is that a complete and total meltdown? Because trust me, unchecked success can be the most dangerous thing for your architect.
And that leads us to this common lie that gets so many teams into deep trouble. You've all heard it. More traffic is always good for business. From an architect's point of view, that is just flat out wrong. Uncontrolled traffic isn't an asset. It's a huge liability. It'll crush your servers, send your cloud bill through the roof, and basically roll out the welcome mat for denial of service attacks.
So, what's the solution? What's our line of defense? Well, it's a rate limiter. And honestly, the analogy here is just perfect. It's the bouncer at your API's nightclub. It stands right at the front door, looks at every single request trying to get in, and decides, you can come in, you have to wait. It's all about enforcing the rules to make sure the party inside doesn't turn into total chaos.
And this is so important. A rate limiter isn't just a technical toy. It is a core business decision. It's your first line of defense. Think about it. It prevents those nasty DDoS attacks. It keeps your infrastructure costs from exploding, and it stops your servers from just falling over. It's not about blocking users, it's about making sure your service stays up and running for all the legitimate users who depend on it.
Okay, so we're all on board with why we need one. The next big question, the first real architectural decision we have to make, is where? Where do we actually build this gate? Because where you put it changes everything. So you've got a few options. You could try to do it on the client side, but come on. That's like asking people to police themselves. It's just not going to work. It's totally unreliable. You could put it directly on the server, but that gets complicated fast. The real sweet spot, the place where architects usually land, is right in the middle, either as middleware or, even better, at the API gateway. Why? Because it creates one single choke point. Every single request has to pass through that gate before it ever touches your precious backend services.
All right, so we've picked the location for our gate. Now we need to give our bouncer a rulebook. What's the policy? This is where the different algorithms come into play. And don't get scared off by the word algorithm. Just think of them as different tools in your toolkit, each one designed for a specific job, with its own pros and cons.
Okay, let's start with the most basic one, the fixed window algorithm. It's super simple. You say, okay, 10 requests per minute. Easy. But there's a huge flaw. Imagine a user sends 10 requests right at the 59-second mark of a minute. Then, 1 second later, a new minute starts, and they send another 10 requests. Boom. You just got hit with 20 requests in about 2 seconds, completely blowing past your intended limit. This little burst at the edge of the window is a classic way for this simple approach to fail.
So how do we fix that nasty edge burst problem? Well, we use a sliding window. The idea here is pretty elegant. Instead of resetting the counter on the minute, the window slides along with time. It's always looking at the last 60 seconds, no matter when the request comes in. So it's constantly asking, how many requests have we seen in the last 60 seconds? This makes it way more accurate and completely solves the edge problem. The trade-off? Well, it takes more memory, because you have to keep track of all those individual request timestamps.
Next up is a totally different way of thinking about it, the token bucket algorithm. This one is really cool. Just imagine every user gets a little bucket. And say every second we drop a new token into their bucket. When they want to make a request, they have to spend a token. If their bucket is empty, sorry, you have to wait. What's so great about this is that it naturally allows for bursts. If you've been quiet for a while, your bucket fills up, and then you can spend all those saved up tokens on a quick burst of activity. It's super flexible.
And on the flip side, we have the leaking bucket. If token bucket is all about allowing bursts, leaking bucket is about preventing them. Think of it like a funnel or a turnstile. All the requests get dumped into a queue, and they leak out the other side at a perfectly steady, constant rate. It smooths everything out. This is perfect for back-end systems that just can't handle sudden spikes and need a nice, predictable stream of traffic.
Okay, so let's put it all together in a quick cheat sheet. The most important thing to remember is there is no single best algorithm. It is always about trade-offs. If you want simple and cheap, go with fixed window, but just watch out for those bursts. If you need pinpoint accuracy, sliding window is your friend, but it'll cost you in memory. Need to handle bursts gracefully? Token bucket. Need to smooth out the traffic into a steady stream? Leaking bucket. As the architect, you pick the right tool for the job.
All right, we've figured out where to put our rate limiter, and we've picked an algorithm. Now, let's move from theory to reality. How do we actually build this thing in a real-world distributed system?
So here's the absolute key to making this work at scale. You're not running one server, right? You're running dozens, maybe hundreds. So each rate limiter can't just keep its own little counter in its own memory. They all have to be synchronized. And for that, you need a centralized, super-fast data store. This is where something like Redis comes in. It's an in-memory database, which means it is lightning fast for incrementing counters. But even more importantly, it gives us atomic operations, and that is the secret weapon against the biggest nightmare in distributed systems.
And this right here, this is the final boss. This is the thing that trips up almost everyone when they first try to build a distributed system. It works perfectly on your laptop with one server, but the second you deploy it to the real world, a silent killer emerges that will bring your entire system to its knees. And that killer is called a race condition.
Just look at this diagram. It explains everything. Let's say our limit is 5 requests, and the current count in Redis is 3. Okay, now watch. Server A says, "Hey Redis, what's the count?" It gets back 3. At the exact same microsecond, server B asks the same question and also gets back 3. Now, server A thinks, okay, 3 is less than 5. I'll allow the request and update the count to 4. But at the same time, server B is thinking the exact same thing. It also updates the count to 4. So now 2 requests have been processed, but the final count in Redis is 4, when it should be 5. You've lost a count. One little error doesn't seem like much, but at scale, this completely invalidates your rate limiter. So how do we fix this race condition? The fix is beautifully simple: atomic operations. When we use a centralized store like Redis, we don't do a separate read, then write. No. We use a single command like INCR, which tells Redis, do the read, the increment, and the write, all in one single, unbreakable step. It's atomic. This means that even if 1,000 servers try to do it at the same time, Redis lines them up and makes sure each operation finishes completely before the next one starts. The count is always, always correct. This isn't optional. It is the absolute foundation of a working distributed rate limiter.
Okay, so let's wrap this up with the key takeaways for you, the architect. First, remember that rate limiting is not about saying no, it's about surviving your own success. Second, place that limiter at a central gateway. It's your strategic choke point. Third, choose your algorithm based on the trade-offs that matter to you: accuracy, memory, or burst handling. Fourth, you absolutely need a fast, centralized in-memory store like Redis for speed and consistency. And finally, and I can't say this enough, your design has to be built from the ground up to conquer race conditions. If it doesn't, it's broken.
So now you know how to build the gate. You've got a powerful system for controlling the flow of traffic. But this leads to an even bigger, more strategic question. We know how to build the gate, but how do we decide who gets a key? Should your free tier users get the same rate limit as your biggest enterprise customers? Of course not. And that's where the real fun begins, where system architecture meets business strategy. But that is a deep dive for another time.
For more tech industry insights for your career or business, go to aaronwoodbuilds.com or subscribe to this channel, link in description. Join the inner loop by getting in the email list. Let's level up our business and career from an architect's perspective.